Hi folks, Mr. Ackerman here. Thanks for watching. This is the supplementary video for Unit 5, Lesson 2. We're going to start talking about collisions and the law of conservation of momentum. So at this point, hopefully you've watched the main instructional video, so you already know a fair amount about what this law says and when it applies and when it doesn't apply. The purpose of this video is to show you some of the things that we would have done in class if we were there together, and also to take you through the lecture notes. So one of the things you're going to find in G-class is not only the lecture notes down here and the main video, but I've also added 4 different videos, which are slow motion collision videos done in my house here with the motion sensor carts that we've used before in class. And I'm going to ask you to use the videos that I've posted here to take some measurements as best you can and see if you can verify the law of conservation of momentum. So we're going to get to that in a little bit, but right now let's take a look at the lecture notes. So the first slide is pretty straightforward. If you watch the main video, you already know that the law of conservation of momentum says that in a collision, the total momentum of the system, so all the objects, all their momentum values with direction considered, because it is a vector, all of that added up before the collision, at any time during the collision, and after the collision is the same if the net external force on the system is 0. So the example that they use is called an air track, and we're not in class right now, but if you can imagine a one-dimensional air hockey table, that's what the air track looks like. So it's basically, there's what we call a glider, which is kind of triangular like this, and it's metal, and it sits on top of a similarly shaped tube, which is kind of a triangular prism. And at one end of the tube, we blow air into it using a vacuum cleaner's exhaust, and the air comes out little holes, just like in an air hockey table, and that causes the gliders to float above the track, and they can move with essentially 0 friction. So I don't have that available to me at home here, but I do have these low friction carts, and if I spin the wheels, maybe you heard that, maybe the microphone picked it up, they spin quite well, and hopefully we can minimize the friction so that the net external force, in this case friction, is very close to 0. Anyway, in the video that you should have watched already, I go through the derivation of the formula, and so the first, or the next slide rather, is just a simple example. It's from the textbook. You can give this a try and check the solutions in the solution manual. The reason I'm not going to go through it with you, of course, is because you have the solutions for you to check and I want to save some time here, but also because I find these types of questions about the law of conservation of momentum pretty straightforward. Like it's usually very easy to solve them because there really isn't much going on. You calculate a vector quantity one-dimensionally before a collision, and then you do the same after, and you make them equal. There's one variable, one equation. It's usually not that difficult to solve. If you get stuck, you can check the solution manual, or you can contact me, and I'll give you some help with that, some hints. What I want to get into is the demo that we would have been doing if we were together in class. So in your course pack, you're going to find a series of lab investigations, and to help you see this a bit better, I'm just going to pull myself off to the side there, and let's take a look here. So scenario A has you colliding, or doing a strange sort of collision. It's a cart is going by like this, and a brick is kind of hovering above it with 0 velocity, and then at some point the brick gets placed on top of the cart, and you're asked to observe what happens and see whether momentum is conserved. And then there's a series of other scenarios, scenario B, and on the next page there's C and D. But let's first talk about the setup. So I've got my table here where I do these recordings, and this is where the track is laid out. You can see there's a carpenter's level on here, which I have a close-up photo of. You can see I've leveled this thing off. I had to put a few pieces of cardboard under one end, and that of course is because I want the force of gravity down and the normal force to be equal. Now I've also taken the mass of the blue cart that you've seen here with previously in this video, and also a red cart, different color just to help keep the two straight. And as you can see, 246 grams for the blue, 248 for the red. So essentially, they are equal mass. So for this first scenario, what we're going to do is we're going to roll the cart and we're going to measure its velocity before the collision. And since we know its mass, we can find its momentum. The brick is going to be stationary, so it has zero momentum. And then the brick is gently placed on top of the cart. And the question I have for you is, why do I have to gently place it? Why don't I just drop it on? So as a hint, I want you to think about the forces that would be acting in each of those two scenarios. Now, once the brick is on the cart, you now have a combined system of two objects that are touching. So you're going to find their total mass and therefore the total momentum. Now the object I'm going to drop on here is actually a 200-gram standard mass, which you've seen me use before. So that's going to go on top of the brick, the cart, which is 246 grams. So just keep that in mind. And now I'm just going to jump into iTunes here, where I have the video. So here's the first one. Let's just watch it together. So you can see the cart's coming in, and I'm holding the mass steady. I'm going to gently put the mass on, and right away, as you might have predicted, this thing slows down. Now, when you're thinking of what the relationship is to real life here, think about the game of football or rugby where people are tackled. One person jumps on the other, and that causes the original running person to slow down. That's one of the applications that you could try to imagine. So just going back to that video again, here's what I'd like you to do. You can play this as many times as you want because you have the videos in G-Class. But what I've done on the track is I've set up these tape markers. It's hard to see. There's a ruler on here, but you can't see it in the video. These are set up every 5 centimeters, so you know the distance. You also know that this is a low friction cart, so it moves with approximately constant velocity. So if you play this, you can say to yourself, I'm going to take my stopwatch, or I'm just going to use the timer down here, and I'm going to have time, I'm going to have distance. That gives me the speed and direction, so velocity before the collision, and then afterwards, so starting sometime around maybe now, you can say, okay, there's 5 centimeters, there's 10 centimeters, and so on, or you can interpolate, you can estimate how far between the tape markers, and that's going to give you an idea so that you can fill in what is the velocity, the prime velocity, which would be a delta d over a delta t, and then of course when you multiply that by mass, that's going to give you a momentum, a prime momentum. And you can do the same thing beforehand. You can say the initial momentum, which is just the momentum of the cart, so that's going to be your 246 grams, or 0.246 kilos, times some sort of delta d over a delta t. Now, just a word of warning. Let's watch this again. If you're watching carefully and you're timing, you might notice that the front of the cart, let's say, crosses each 5 centimeter spacing in less time at the beginning than at this point. And that is, of course, because there's friction and the cart is slowing down. So this is not the world's most careful law of conservation of momentum investigation, but there is a global pandemic, so I apologize. This is the best I can do for you right now. But I think if you make sure that your measurements are done as close to the time of collision as possible, so don't measure from back here. Wait till this thing gets a lot closer, and therefore there's less time for it to slow down. Maybe begin here, and there's 5 centimeters, 10 centimeters. You could time that with your phone and get a pretty good idea of the velocity prior to collision, and then the collision happens right now when the front of the cart is here, and then maybe you could measure the 5 centimeters, the time to there, and that'll give you an idea of the velocity after. And then you can ask yourself, conclusion, is momentum conserved? Look at the momentum here, look at the momentum there, and make a conclusion. All right? Let's move on to scenario B, which is kind of fun. There's 2 carts with a loaded spring, a compressed spring between them, and the spring is released, and as you might guess, the carts go in opposite directions. Now this time, one of them is the blue cart, B, and one of them is the red cart, R. Note there's a slight difference in mass. This one's 0.248 kilograms. Not a very big deal, less than 1%, but let's be as careful as we can. Let's go take a look at that video to see what's going on. So this one, I release the spring and they go in the opposite direction. One more time. Now, if you wonder why am I using the mass, there's just a little pin here that needs to be compressed in order to, or depressed rather, to release the spring, which is in here. And I like to hit it with something that's got a little bit of heft to it so that it definitely releases it. And you can see that the masses, the carts go in opposite directions. That's Newton's third law. The momentum prior to the collision is 0, and then afterwards, away they go. Same sort of thing. Pick a small distance interval immediately after the collision and measure the time for blue, and the same with red, and then make your conclusion, is the momentum conserved in here? Remember, momentum is a vector, so while one cart is going this way, and the other cart's going that way, those have, one of them is negative, so you might want to say something like positive to the right. And by the way, I just realized that this was actually the red cart there, and this was actually the blue cart, but no bother. I'm sure you guys will figure it out. Okay, let's move on to the next one. Scenario C, 2 gliders are on an air track. Glider 1 is pushed toward number 2, which is initially motionless, and a collision occurs. This is like a rear-end collision for cars, and I'll show you what the video looks like now. So here the red one's coming in. There's a spring bumper ready to go here. We're going to measure the distance and time just before collision, and then for the blue just after. Notice this one comes to rest. So we actually have an easy measurement here. 0 momentum for blue prior to the collision, and apparently 0 momentum for red after the collision. So the thing you need to do here is now go back to this. Draw a picture for before the collision, draw a picture for after. Figure out your momentum values. So you can say something like P blue equals mass blue, velocity blue, and that has some value. And then P red equals mass red, velocity red, and that's going to give you some P total value prior to the collision. And then you're going to do the same for after. So you'll have P prime blue, the final, and then you're going to do the same for the red, prime, and you can add those up into P total prime and see what you get. Are these two equal? Or not? If they're not, which one is greater than the other, and why do you think that is? So start thinking carefully about what's going on here and trying to make some, trying to get some meaning out of that. The final one is similar to scenario C, but this time the objects stick together, and this is a really interesting scenario. I'll show you what it looks like first, and then we'll talk about some applications. So here we go. Oop, I already had that one set at the beginning, so here we go. Blue is at rest, and now I don't have the spring bumper set out here. I have a Velcro bumper, so it's going to stick, as you're going to see in a moment, and then the two objects move together. Now, what I want you to think about here is when would this actually happen in real life? So let's think for a moment about things that stick in a macroscopic collision. Maybe it's back to the rugby game or the football game where people are tackling one another. Maybe it's an example of, you could think about cars that are crashing, and they actually sometimes their bumpers kind of get tangled up and they intertwine. Let's think about something microscopic. Maybe it could be an atom and another atom, or two molecules coming together and joining to form a larger molecule. So there's actually some pretty cool applications here that physicists really do use when they're looking into momentum and how it applies. Anyway, That's it for this mini lab here. What I'm going to try to do, and I'm not certain I can get this done, but I will try, is to set up my motion sensor software to make much more precise and accurate measurements for you. But that's going to take me a few days and a little bit of work, and I'm not sure it's going to happen, but if it doesn't happen, this will suffice because it will give you an idea of exactly what we would have been doing in class if we were there together. There's one last thing I want you to take a look at, and this is a challenging example. As a joke with my terrible humor, I call this a sin challenge, Sir Isaac Newton challenge. I like to say it would be a sin not to try this one, but this is from the Sir Isaac Newton contest one year, and let's read it. There's a competition between two teams of physics students, and each team has 3 members. Each member has a mass of 60 kilograms. They're going to take turns running along a cart, a frictionless cart, on a horizontal track, and by running one way, they're going to push the cart backwards. That's Newton's third law. So try to imagine that this cart, let's say it's a lot bigger than it really is and could actually hold people. Maybe a skateboard would be a good idea to think of. And so let's see, can you guys see that? Imagine if you were on this and you started running this way to jump off, you would push the cart that way. So that's the idea of what's going on here. By having the people move this way, they exert a force backward, the cart goes backward, the students go forward. Now, team number 1, all 3 students jump at the same time by holding hands. Team number 2, first person goes, and the other 2 stay still. Now the cart moves a bit. Then the second person runs, and the other remaining person stays still, and the cart moves some more. And then the third person jumps, leaving no one behind on the cart, and the cart gets its final push. Which team gets the cart moving fastest? The people who jump all at once, or the people who jump one at a time? Here's the twist in this one. When they tell you about these runners, they tell you that they run, each of these people, whether they run together or not, they run at 10 meters per second with respect to the cart. Now remember, we've talked a little bit about how if you don't read questions carefully, you might miss wording that gives away an important tip. With respect to cart should get you thinking of frames of reference. Now what are they talking about here? When we say that someone can run along a cart at 10 meters per second, you go, okay, fine. But remember, starting to run on this thing gets it moving backward. So in the frame of reference of Earth, which is where we're measuring how fast did the cart get moving, that's how we pick the winner, right? We need to figure out, okay, if you can run at 10 meters per second this way, but the cart that you're on is now moving backward, how fast did you move relative to Earth? So you've got to start thinking in terms of, oh, there is a cart, remember this stuff from Unit 1, and there's Earth, and there are students. So for example, the velocity of the cart relative to Earth is not the same as the velocity of the students relative to the cart. And of course, there are other letters, there are other combinations you've got to think of. There's a little blurb down here to remind you, because I know it's been a while since Unit 1, so I'll just put that in here. Unit 1, you want to look back at section 1.5 in the textbook to get an idea. But what I've done is, in the next slide, which you don't have in your lecture notes, I'm going to show you a little bit to help you through this. But before you look at that, I want you to try this on your own. Here, so pause the video, give this a try, and don't look until you've given it a shot. Okay, here we are now. Let's take a look. I've drawn a before picture and an after picture, which you should always be doing in these kinds of problems. In the beginning, the cart velocity relative to Earth is 0, the student velocity relative to cart is 0, and the student velocity relative to Earth is also therefore 0. The total momentum, which is the cart and the student momentum, is therefore 0. Positive direction is to the right. Now, at the end, these guys all together jump off, and they are moving relative to the cart at 10, but the cart is moving backward relative to Earth. It's got a prime final velocity backward. So the students have a prime final velocity forward, which is not 10. So I'm going to move myself over here. Pardon me for a sec. Here we go. If we write out the momentum of the students in the cart, and we remember it's a prime momentum, and it has to be in the Earth frame of reference, which is where we measure who gets the cart moving fastest, then this is what you come up with. We have to realize that the student velocity relative to Earth is the student velocity relative to cart plus cart velocity relative to Earth, and that will be positive 10 plus whatever velocity the cart recoils backward with. We run that through the calculation and we arrive at an answer. I'll let you look at the math on your own. The interesting thing is, what would have happened if you solved this problem disregarding the fact that this is a frame of reference issue? If you ignore the frames of reference information, and you therefore screw up the question or your solution, you would have written something like this, which gives you a very different number than what is actually the case. So, my last thing that I want you to do once you've understood this is repeat for team number 2. Now remember, team number 2 goes one at a time. And that means, yes, unfortunately, you have to do this calculation once for the first runner, another time for the second runner, and a third time for the last runner. And you want to see, is the final velocity of the cart the same, minus 6 meters per second, or is it faster or slower? Which team wins? And when you get to the answer, which I'm not going to tell you yet, you're going to see something interesting, which actually has a relationship to things like shooting a gun and launching a rocket. More on that later. Sorry for the long video, but this is a major lesson. It's one of the most important ones in the entire course. Hope you enjoyed, and if you have any questions, message me. Stay safe. Bye for now.